Started to be efficient. So the next session is Rodrigo Alonso. He's going to be talking about the Higgs effective field theory, which is kind of complementary to the SNAP approach. And Rodrigo, take it away. All yours the floor.
Thanks, Mike. Alrighty, so I'm Rodrigo Alonso. I'll be teaching you for these 4 hours about Higgs effective field theory and the uses of geometry in it. And I would like to thank the organizers for having me talk about this field of physics. So a few words on what this is going to look like. You can, of course, stop me at any point for questions, but it might be challenging over Zoom, so you can also email me questions. I'll do my best to get back to you. Now, there's PDF lecture notes for these lectures. You can find them over here in my webpage. There's also a link on the school's webpage. And what I've gone for in these lectures, partly because that's the way I would have liked to be taught myself, partly because that's the way we teach here in England, is not so much going for extent or trying to cover a lot of topics, but rather being hands-on and working out examples about a few key concepts of the field, so that you come out of here feeling you've understood some of it in depth. And for that, in the PDF notes, let's pull them out. You'll see at times that there's parts of the text in between these teal lines. These are exercises for you to try out and derive results. I've tried my best to make those accessible and give you hints and clues on how to do them, but it might be that there's some difficulties in it, so I can give you the solutions later, or you can again email me about it and we can have a session in which I answer your questions or solve some of the problems you've had trouble with. And also don't hesitate, I'm sure there's typos here and there in my notes to tell me about it. I'll be updating them at this address. And about what you can expect to get out of here with, well, I'll be talking about Higgs effective field theory, of course, and you'll hopefully become acquainted with it by the end of it. Some of the main topics we'll be talking about, and I hope you learned, are the dynamics of non-Boston bosons, geometry and the scattering metrics, and this dichotomy of effective field theories, linear versus nonlinear, or in other words, standard model EFT, which you've already been introduced to, versus this modulo Higgs effective field theory, modulo SMFT, that is to say, what is in Higgs effective field theory that is not in standard model EFT, and the experimental prospects to tell these two apart. Very well. What we'll learn about in these 2 lectures covers roughly the first 3 chapters of the notes. And in one sentence, what we'll be doing is building Higgs effective field theory from the bottom up, as you do in, or you can do in EFT. It's not the only way, but it's the use of it. And later on, we'll move on to more advanced topics. Okay, again, you've been introduced to effective field theories, and you know some about it. And some of the things I'll talk about here actually already been touched upon by Professor Trott, but I'll be coming at it from a different angle, or I'll be using that previous knowledge to push ahead. And after all, it is me giving this lecture, so there's going to be a bit of my take on things. I'll try my best to be impartial. But if you ask me, what are the most prominent properties of effective field theory, I would say that within its assumptions, because there are assumptions, which is basically a separation of scales. But within those assumptions, effective field theory is very general. It's further unbiased when used in full generality. But it's of course also good to keep in mind that it's only valid in a limited regime. It's not valid everywhere. And at some point, some other description, hopefully a deeper description of nature, takes over. And in turn, effective field theories don't ask for much for their formulation. You don't need much to specify what the effective field theory is, but you need some things. You need to know what you're talking about, what is the particle content that is out there, what are the symmetries of the system to implement them in your dynamics. And finally, you do need, as everywhere in physics pretty much, an expansion parameter to organize your computation. And so we'll be following this three-step program to build our Higgs effective field theory, just like you could build any other effective field theory. So let's try and start with, in some sense, the simplest part of the particle content that we know is out there, and it's nice organization under the central symmetry of nature, excluding general relativity for now. We won't be talking about gravity at all in these lectures, so we'll always leave it aside. But if we leave it aside, the known forces in nature derive from the gauge principle, and in particular from the gauge group that we wrote in here, SU3 for unitary three-dimensional determinant equals 1 rotations in complex space, SU2 left for weak isospin group, and U1 hypercharge for that abelian part of our group. And as you might know already, knowing the gauge group tells you what is the spin 1 content of your theory, the massless spin 1 content of your theory. And so color comes with 8 gluons for the 8 generators of SU3. Weak isospin comes with 3 gauge bosons that will denote W, I in here, alpha and I are indices here. And hypercharge is has its own gauge boson that will denote B. Now what we call matter, as opposed to those gauge bosons that come from the gauge principle, will be organized in here in these doublets. Does that not mean that we're taking the right-handed doublets in particular any series, but it is a useful device to write our theory down. And we classify this matter content according to the transformation properties under the gauge group. So for example, we'll denote QL, the left-handed quark doublet with an up and a down. And then each of these has a further flavor index, but we won't be talking much about flavor in these lectures, just so you know it's there. And then the same quark doublet is a fundamental under SU3. You can think of it as a complex vector that is rotated by these transformations. It is also fundamental under SU2 left, has this other index that is acted upon by weak isospin and has a hypercharge of 1/6 in my convention anyway, or the convention that we'll be using here. Then we have the right-handed quarks, up and down right-handed, that I arrange in this right-handed doublet. They are in the fundamental representation of SU3. And when you write down its hypercharge, you can use this Pauli matrix which is nothing but the diagonal 1 minus 1 in 2 dimensions, to note that right-handed up quarks and then down type right-handed quarks have actually different hypercharges. But it's useful to know that it's the identity in this two-dimensional space with the same hypercharge than the left-handed quarks plus an addition that is proportional to this poly matrix over 2. And so the same transformation properties can be written down for leptons that we arrange in those doublets as well. And further, I'm going to be a bit explicit in the beginning and maybe go over some things that you already know, but it's good to establish a notation and get everyone on board. So a bit of definitions here, or making specific what we mean by this gauge symmetry action. So let's take the action of the symmetry group given by some element group G. In our conventions, this is a unitary matrix in whatever representation, so G dagger G equals 1, and we can use an exponential parametrization in which this is given by some parameters epsilon times T, which are the generators of symmetry. If we're talking about, say, the isospin SU to left, this will be the poly matrices. The way we act on, let's say, that left-handed quark doublet, we will denote this left-handed quark doublet sub G as the left-handed doublet acted upon by the symmetry, and you already know this. This is as simple as that group element G multiplying that quark doublet. We say this is a linear transformation property. And further, if we expand out that exponential, we'll have first the identity and then a term proportional to the generators multiplying the quark doublet. We'll denote delta sub G on Q left, this infinitesimal action on our quark doublet. And now, as you know, the need for gauge covariant derivatives, because we want objects to transform covariantly to build invariant. Being very explicit, do the same thing. Now we compute the transform derivative of the quark doublet. We'll have the derivative of the quark doublet transform, but also a derivative of the group element, because this is a gauge transformation of these epsilon parameters depend on X. And that doesn't transform as we want it to, with just the group element times the original object we were looking at, which has the fix that you already know about. We simply write a covariant derivative, which will have those two same terms there, but in addition, we add this other piece. Let me just note it. There's some gauge boson A mu, with some coupling G, and there's some implicit generators in there. It's self-transform and times this group element over Q left. And so things will transform as we want them to if the transformation of this so that we can cancel this sign and cancel that one.
We can't really hear you at the moment. Isn't the pause? Strike two. Right.
Good. Sorry about that. Let's hope the connection is stable now. All right. So, I mean, this is something you guys probably already know. These are the transformation properties and the interaction of a gauge covariant derivative that we need for covariant objects. And what this ends up looking like for a gauge group that we specify later is a covariant derivative acting on that quark tablet, which you have that first piece, that ordinary derivative. Then, as we said, this quark tablet is a fundamental undercolor, so it's going to be the Gell-Mann matrices for SU3 with the gluons and the strong coupling that we call G sub S. Then the poly matrices with weak isospin bosons with the weak isospin coupling that we call G, and the same for the hypercharge with G prime for that coupling. And this does now transform covariantly as it should. And as you know, this demand of having objects transform covariantly is something that we need to build invariance, and it applies here. It's in general relativity, and it will apply also when we talk about the geometry of field space. Very well. So this is all the nice story about the particle content, so to speak. It accounts for a lot of the interactions we see out there, and in particular the interactions of matter with the known forces. But as it happens, this is not the symmetry that the vacuum displays. Instead, in the vacuum, we don't see the whole electroweak theory, but only U1 electromagnetism. That's why we talk about the two different bases. This first basis with the W bosons and the hypercharge boson. In reality, down there, we see them arranged differently with W plus minus and the Z boson and the photon that we call A mu. This, well, this allows for masses for fermions that we know are out there. This requires that some of the H bosons get a mass. But the crucial difference between a massive and a massless spin 1 particle is that a massive has 1 more degree of freedom. So the particle content that we wrote before is incomplete. We need these extra longitudinal degrees of freedom for the W plus minus and the Z. And these are the goldstones of our theory that live or belong in that same space where the broken gauge bosons live, and that's none other than to let U1 modulo U1 electromagnetism. And out of these, we will get those longitudinal degrees of freedom for the W and the Z. Now the question is, how do we go about describing such a peculiar looking space or scalar fields, so the scalar fields in such a space? And for that, what we will go through in this lecture is, or the path we'll choose here is the so-called Coleman, West, and Sumino procedure that was laid down some more than 50 years ago now. And instead of giving you the formulation for the electroweak theory only, I'll give you the generals, and then you can use this, and we can actually use this later on for other theories. So let's start with the definitions. Let's take instead a group G, or this calligraphic G, to distinguish it from the other one, broken to a subgroup, fancy H in here, with the generators of the whole group being capital T, with some index alpha. The generators of the broken group we'll call X, with some subindex capital Latin letter A. And then the unbroken part of the group will be little t, with some subindex lowercase Latin A. Okay, so broken X, unbroken T. We can further choose our basis such that the trace of any two operators is a Kronecker delta. In particular, this means that the broken and unbroken generators are orthogonal with this projection. And then we can lay out the Lie algebra with F, the structure constants. And we first write down here the commutation relations for the unbroken generators that map back onto itself. So there's the structure constant, but only with unbroken generators in there. That is because if we had assumed there was also a contribution to the broken part, the subgroup H wouldn't be closed, so it wouldn't define a group. And we'll have to look again at what we mean by H. So just from the group to be closed, we demand that this term is 0, or those structure constants. But this also tells us something about other commutation relations, in particular if the group is compact. The structure constants are completely anti-symmetric. So when we write the commutation relation of an unbroken and a broken generators, we can say that it projects onto the broken generators, but not onto the unbroken, because these, we just said that these structure constants with 2 unbroken and 1 broken index vanish. So this, by that anti-symmetry, fully anti-symmetric relation will also cancel. And this will be 2 relations that will be really helpful later on. Now we can always write any element of the group. I know I'm giving you quite a few definitions, but please bear with me. We'll get to the physics soon enough. Any element of the group, G sub T, can be factorized into an element of the broken part of the group and an element of the unbroken part of the group. And so just like we did for that gauge transformation, we can write for constants as some transformation in the broken part of the group that we call C as the exponential of I times pi bar, where pi bar is just the contraction of 4 constants that we'll call pi with an upper Latin letter A contracted with the broken generators. And V is just the scale that we need here for dimensional mass dimension reasons. And so how does this transform? Sort of have the matter, the content, the particle content there, but how does this transform under the symmetry? And for that, we just note that the group composition law, if you have 2 elements, G1 and G2, the resulting element is the product of the 2. So we can think of G1 as our original C matrix and G2 as G, this group we're acting with. And so from C, we'll go to the product of G times C, simple enough. But now we have to project this back into the broken and unbroken parts of any group element. So we'll define this as a transform field C times a unbroken transformation G, just because we know we can always write it like that. But then that will tell us that the transform C reads G times the log C, and this unbroken group transformation dagger. Or if we expand this to be infinitesimal, C plus I epsilon T, just like we had for G transform earlier, and minus I C on the other side, that unbroken group transformation that nevertheless depends on the constants themselves, and it projects only to the unbroken generators. So this function beta in here is a function of C that we don't know a priori, but we can determine as we'll make explicit in a minute. All right, so then that gives us an implicit form of the scalar transformation, but it's not an easy to see how that transformation is acting on our fields phi. And to see that, we'll try and do an expansion and try to recover some intuition about it and some things that you might already know. So let's assume that the field or goldstones P bar in particular transform under G have an expansion in which we get the first point and then sort of the first term in that epsilon series that we call delta G pi bar, just like we did before. And now we write that first variation of C, or with that group action times C dagger. We take this combination because we can reduce it always to an element of the Lie algebra. This will always be generators, as we'll see explicitly now, because we can be more explicit and say that that variation will be just the derivative with respect to pi bar times that variation. This is just a chain rule, and that exponential for C and the inverse of the exponential there. And on the right-hand side, we'll have again those T generators in between those two matrices. And as it happens for the unbroken part of that transformation, because we're multiplying by the left, we'll cancel that factor of C in there. So we just have epsilon times beta T. And the way this looks like using the Campbell houses of formula. I'm not being very explicit about citations. In fact, I'm missing all of them. They're in the notes, and also you can have, I mean, in Professor Trott's slides, I see it was very thorough with citations. You can see them there. But what this looks like is an infinite series on the left-hand side of commutators minus I pi bar minus I pi bar with that variation in the core, where we have this 1 over n, there's a sum over n, and there's n minus 1 nested commutators in there, which equals on the right-hand side another infinite sum of, again, those nested commutators, but now at its heart, I epsilon dot t. And since we added, we can also expand this beta function in a series on our field. Where this one here is n times. So it is a rather cumbersome looking formula, and that's because finding the transformation properties of constants is no easy task. Being explicit, this is indeed a nonlinear transformation that is quite complicated, and it's not possible in general to solve for it. We have the magnitude we want to find in here, which gives us how the Goldstones transform, but it's inside all of these whole series of nested commutators. And then the right-hand side is itself also written in terms of the series, which is not easy task to solve, but the first exercise or problem that I invite you to do in the notes is to expand this and retain only terms up to order pi, so discarding terms of order pi squared, and then solve for this transformation of the Goldstone delta G pi to second order, that is to say, we pick up orders of pi 0 and pi level. And from here already, this is the formula that you get if you go through with the exercise. We get a first piece, which is independent of the Goldstones themselves. This is just a shift proportional to the decay constant, I will call it B in this case, and these parameters of pointing in the broken group direction. And you've seen this before, I'm sure. You know that an axion transformation is a shift, and that is also true of any Goldstone in this expansion. The first element in this expansion is just a shift in the broken group direction. The difference is that an axion is an abelian symmetry, so it has no structure constants, and that's where the series stops for an action. That's nice and simple enough. But if you have general Goldstones, you're going to have also a linear term proportional to the unbroken part now, with this epsilon parameter pointing in that unbroken direction, and also a broken component and higher orders. In general, quite complicated relation. Okay, so that's for us to get a peek of how these guys transform. We say they transform non-linearly. But when we write our action, we're not going to do, or we don't have to do any expansion. We want to write everything fully invariant and without no approximation. For that matter, if we're going to build invariant for action, with C alone, you cannot build anything. You can take C dagger, but that's the identity, so it doesn't depend on the field, which is a restatement of Goldstone bosons having no potential, exact Goldstone boson. So we turn to derivatives, just like we did for the standard model. And we now take the transform derivative of C again times C dagger. It is a useful construction. And when we do this, we simply write in here the transform C and here, and we'll pick up the usual derivative acting on the field itself, where the factors of G will cancel out inside. Then we'll pick up the derivative of or transformation G, which is the very same one that acts on those quark doublets that we talked about with G dagger, and we have seen this before. Actually, we know how to cancel that part. Can just add up gauge bosons that we did for other guys. Now the nasty piece is the last one. When you pick up the derivative of that unbroken element with respect to X, we can do as we did before and use this formula of nested commutators. At the heart of it, there's going to be the derivative of epsilon times beta times t. And this will pick two pieces. The derivative of epsilon is parameters of our transformation that depend on X, but also that function beta of the Goldstone. That would actually require adding a new gauge, well, not a new gauge, well, yes, gauge, but a new spin one boson that we weren't looking for. And it's indeed part of the UV, not the IR. So we will do away with it. We only want the Goldstones and nothing else. And the way to do that is to realize that complicated as this expression is, what it always boils down to is a commutator of unbroken with unbroken that we know takes us back to unbroken because the group is closed, as we said in there. We had one nested commutator of T's. This will be T again, and the whole result will go to T. So all of these series, complicated as it is and requiring this cumbersome analysis, it always projects back onto the unbroken group or the unbroken Lie algebra. So we can just project it out and forget about it and take the easy piece. For that, we define the current J, which is simply the trace of that construction with the covariant derivative times the broken generators XA, and for all we care, we're only going to pick up that piece that was just like an ordinary derivative, covariant derivative in our original theory. All the other complicated stuff in this is in this other current B. And before we run ahead with our current J, we should first check that it's closed under transformations, that these two currents don't mix. I mean, something that is, again, outlined in the notes, but if you contract current J with the broken generators, you can see that it transforms with that unbroken transformation dagger on the right and that unbroken transformation on the left. So here, at long last, we can write an invariant because we have found an object that depends on the Boston bosons and that transform in a well-defined covariant manner. So we can go ahead and write this term. The normalization you cannot guess on your own, but you can see that an invariant that we can build with that object. Nothing we can build with the object itself, but because of that Lorentz, we add it up with itself in the square. We get something that looks like a kinetic term. And indeed, this, well, it has to be what I wrote in there. I will have something like the trace A. All right, so that is the first term in our EFT, if you like, for these Boston bosons. That will give us a kinetic term, but also given that this Xc is an exponential of the boson, there will be a whole tower of operators, or in an expansion, the whole power series of powers of our Bostons, as we'll see in a minute. At least we've succeeded in writing invariant action for dynamics. And we shall now apply to the electroweak theory. So for the electroweak theory, we have a useful embedding that actually means no lack of generality, as we'll see in a minute. But rather than the pattern of SU2 cross U1 broken to U1, we can embed that U1 hyperchar in SU2 right. We can have this be pointing in the direction of the third Pauli matrix, basically. And the same for U1 electromagnetism, but now for SU2 vectorial. So the simultaneous action of left and right. If we do that, our broken generators are in the axial direction, and we can write that in 2 times 2 block as a half of the Pauli matrices and minus the Pauli matrices. So all in all, this is a 4 times 4 matrix that we can break down into those two blocks. Those are the broken generators. To obtain Xc, we just exponentiate them contracted with our pi fields or Boston bosons. That exponentiation will maintain that block diagonal form, and let me call U left and U right each of them. They are unitary, and the same for the right-handed. And following our steps, now the transform C has a group action on the left, or the whole of it, and then an unbroken part of it acting on the right. It will look something like this, again with left with L and R unitary matrices. And on the right will be some action of the unbroken part, which is just that SU2 vectorial, which acts simultaneously with the same unitary matrix on both entries. Now, I don't know if you can see it from here, but there's a shortcut to write our action in this case. And that's because if we go back to the discussion about bosons that we had, all of the complications were coming from that Boston boson dependent piece, transformation on the right. In this case, excuse me, this V dagger that acts on both of or 2 times 2 matrices. So we could follow the steps that we've done before to get rid of it, or we can also realize that the following combination does away with that V matrix. If I take U left and then put U right dagger times it, when I transform U, it will pick up that left-handed unitary matrix on the left, U left, and then that unbroken part of the group on the right, but that's precisely what we get on the right-handed matrix there. So these two cancel out to give us transformation that depends on left and right, those unitary rotations, but those were not field dependent, unlike C, like P dagger here, that depends on C. So that let us write or action in terms of this object U without having to resort to defining currents. Now we simply have to specify how our covariant derivative acts on U, given that we know the embedding right here of the electroweak group in this larger group. We can make it explicit and just write, gonna have that ordinary derivative first, and then we Kaiser spin on the left. And on the right, there's that R dagger here. You might have seen that already, and I just did, but it's R dagger when we take that dagger, and in here, instead we'll have it on the right, G prime, sigma 3 half times that the boson beam. So it is a bit peculiar in the sense that for every other representation that we wrote, that covariant derivative acted only on the left. Here it also acts on the right, but at least it's a Gaussian independent transformation, and for all intents and purposes, this derivative is just like the ones we wrote for the left-handed quark tablet and the other ones. That, by the way, I think Professor Trott called capital sigma in his slides. The same thing we're talking about here. So now we get to a Lagrangian that we build with that matrix U. The equivalent of that kinetic term that we wrote for constants is now the derivative acting on U and U dagger. This gives us an invariant when we transform it. We take the trace of it. Now the normalization is slightly different for reasons that we'll see. We put it together with the rest of matter with the gauge kinetic terms. But this is F denotes all the field strengths, and there's a generic sum here with the gauge group. And then the kinetic term for the fermions. And there's this possible coupling of fermions left and right with this matrix U. You can check yourself that this is invariant. In particular, remember on this U that hypercharge was acting with that Pauli matrix sigma 3. The action on these right-handed fields we wrote down also in terms of a Pauli matrix sigma 3 and another piece. So it's a non-trivial exercise to check that indeed that the whole operator is invariant under our gauge symmetry. And this, excuse me, this Lagrangian does what it's supposed to do. It describes massive gauge bosons and the gauge interactions of matter, and allows for masses of fermions as well that would be proportional to those. These Yukawas are some constants in here. You can see how the masses come about when you expand that covariant derivative of U around the vacuum, which in our pi and coordinates would be pi equals 0. That's what we're meaning here. We'll pick up a term that is proportional to sigma 3. with this combination of the third weak isospin boson and the hypercharged boson that defines our set. And I'm using this also to define our weak mixing angle. Excuse me, and then there's the W plus and minus H bosons that we write here in terms of the latter term, which is just 1, 1, 0, 0. That guy there. And you expand the kinetic term of the Goldstone bosons starting with this term in the series, and you obtain masses for the Z and the W. In particular, the reason we were putting this V square in here, because we recover the relation of the mass of the W square as that weak isospin coupling square, the lecture with Bev, which is here 246. Anytime you see V in these lectures, it will be 246. And the mass of the fermions is recovered as that electroweak Bev over square root of 2 times the Yukawa coupling, again in this convention we're using here. And I think it's, well, I just made this note here, memories, because I think it is, it gives some perspective to think about how I remember when I was a student in school some 10 years ago. One other of the teachers in the school, actually, Alex Pomaron, presenting this Lagrangian to me. This was 2012, or to me, to all of us in class, and saying, this is really as much as we know about nature today, because the Higgs boson was still not discovered, and that was still just a hypothetical particle. Here I am presenting it once again. But of course, we've made progress in them, and we know more about it. Before we go on, let me have a note about custodial symmetry and the fact that even though we wrote things with these matrix Q that transform with well-defined properties under SU2 left and SU2 right, it needs not be respected, and it can be broken. A way to write this with a matrix T, in the note this is bold font T, in which we can just stick polymetrices in between a U and a U dagger, because this polymetric in this space is proportional to weak, to hypercharge, the hypercharge generator, excuse me. And so the way this will transform under G will be with hypercharge group elements on the left and the right dagger that commute with sigma 3, and then just leave us with L. It will be just that left-handed transformation T and the left-handed transformation dagger. So this is what we call a triplet, or we can build an operator such as the trace of that T. This is not the generator, sorry, I was trying to write it differently. The trace of that T with our current of Goldstones, D mu, squared, again, to make it a Lorentz invariant with this free coefficient. And that's another thing that you can try out in the notes. You can write this operator and again expand around the vacuum, those properties, and you will see that this contributes an extra piece to the set boson mass. And the reason we say custodial symmetry, it's a good symmetry in the scalar sector, because the rho parameter, which is this ratio of the masses of the W and the Z times cosine of the weak angle squared, is really close to 1, down to the 10 to the minus 4 level, which allows us to derive, or you can derive, that's what I asked you to do there, a bound on this epsilon custodial violating parameter in there. There's more guidance on how to do this in the notes.
Rodrigo, about 10 minutes left, just to give you a heads up.
There's a what, sorry?
About 10 minutes left.
Ah, okay, good. Thanks for that. All right. Now let's talk about something in this last 10 minutes that you've already heard about in the SMEFT lectures, but apply to the Lagrangians that we were discussing in here. This theory that we just wrote down, as good as it is to describe low energy physics, has limited validity in a very explicit sense, where we know where it stops being valid, the reasons for which we'll explain right now. And we'll see by looking at longitudinal boson scattering. Again, this has already been mentioned before. We can use the equivalence theorem that tells us to compute that longitudinal scattering. You can look at the Goldstone-Boson Lagrangian and pick up the most the interactions with the most insertions of momenta. In this case, in our case, those will come from that very kinetic term, higher powers of that kinetic term, that we can write explicitly for both of theories. So if I go back and stick to the CCWC formulation, I can write, I did write explicitly my broken generators in there. I can write again that C dagger C, this is what this is, neglecting gauge bosons that we can do in this limit for the equivalence theorem, as this series of nested commutators there, and expand it. Or we can do it with what we call omega field, in which we use something like a square root parametrization, well, not something like the square root parametrization that was introduced by Weinberg some time ago. We can parameterize this unitary matrix with the Pauli matrices times these omega fields around, they have an index 1, 2, 3 for the Pauli matrices times the identity and the square root of 1 minus omega square root of b squared. And then writing that explicitly actually looks quite simple. You can do it yourself, and you get a term that is just an ordinary kinetic term, but then a term with something that looks like a pole here in b squared, although there's no real singularity at that point. It's just a feature of our parametrization. And we can go ahead and not only see for ourselves that these amplitudes grow with center mass energy S, but also do it twice with each of these theories that should give the same result. But we can check explicitly that they do give the same result and convince ourselves that all of these talk about field reparameterizations is actually a real thing. And that's the third exercise that you can try out in the notes, which is to say, compute that scattering contribution with the equivalence theorem for both theories. So you can do this part again yourselves, and I sketched how to do it. You have to compute the 4 pi term in that expansion of our kinetic term. You would obtain something like this, a piece like this in the Lagrangian. Then we further want to look at, in particular, W plus boson scattering. So we define the charge states as this combination of pi 1 and pi 2. We can do the same for those, for the field variables omega. In that case, it looks slightly simpler. And we again define the plus and minus for the charge components with that simple definition. And then what I ask you to do is compute the Feynman rule for this vertex, which we have, this is the direction of time. In which we have a pi plus particle coming in with momentum p mu and a pi plus particle with momentum k mu, going to a pi plus particle with momentum p prime, and another one with momentum k prime. Not sure how familiar you are with deriving Feynman rules for terms with derivative. Just remember that basically when you have a derivative acting on a pi plus field, it excites out of the vacuum a momentum, a particle momentum I minus I p mu. Whereas if you have an outgoing particle momentum p prime, it is the pi minus field that excites a particle, and out of that derivative you will get the opposite sign, I mu prime. In this exercise, because we're taking that equivalence theorem and that limit, we neglect all masses, which in particular also means that the center mass energy S twice P dot K, S plus T plus U being the Mandelstam variables adding up to 0, and you'll have to use all of those to obtain the final result, which I will give you after the break, I think, because I'm nearly there now. So we'll be stopping for 30 minutes, I guess. No, Mike?
Stop if it's for you. We can ask questions, maybe. Do you have more that you want to cover, like a minute or two, or you good?
Well, okay, let me give you just, I have what more, 2 more minutes?
Yeah.
Okay, well,
Talk fast.
right. No, I just I'll just give you what this looks like. I was thinking maybe, I don't think I'll be quite a feature if any of you did this in the 30 minutes of break, but who knows? The answer to this exercise, when you do it for both of them, you get the same result, and you get an amplitude. In our conventions, by the way, we define the S matrix as the identity minus I times the amplitude A, and then a conservation of total momenta. Or with those conventions, the amplitude that you will get for both cases being the same again is the central mass S over V squared. And like I said, that's a great exercise to convince yourself that those two Lagranges are the same and that field definitions don't matter for the actual physics of the problem. And well, after we come back to the break, we'll talk about exactly why is that a problem. You already know, but just to go a bit more in depth about it. So yeah, let's leave it here, and then we'll take over with unitarity, and that will be at 40 past then. No?
Might be some questions from the audience.
Oh, right, yeah.
Thank Rodrigo for his first lecture. Questions?
Thank you.
I have one I could ask. This is a quick one. With the custodial symmetry constraint that you're putting on, so is your perspective that all the sources of custodial symmetry breaking that can appear in also for operator form, we should just basically accommodate in that way, or you just think that the one that you pointed out related to the scalar sector is the one that's really the most concerning in terms of custodial symmetry violation? So once you deal with that, you don't have to really worry about other aspects of custodial symmetry violation.
Right. So yeah, about custodial symmetry. This. I think I could not catch everything you said, but I think you were asking if I think this one observable that I looked at is representative of all custodial violation in other places too.
Are you worried about other tunings that you have to do to suppress other effects, or is this, you think, sufficient? You just deal with this?
Yeah, I would think that in the spirit of EFT, I've just defined and talked about one of the operators that violate custodial symmetry. And while this is a good argument for its conservation, and if you work out the numbers, it's a really strong bound on that coupling, that doesn't mean that I can go on and forget about any other custodial violation in the form of other operators, because in other sectors, I could have extra sources of custodial violation. And again, in the spirit of EFT, you should inspect all of the possible terms that are in there, all of the ones that violate custodial symmetry. Having said that, asymmetry is one of the few good reasons that lets you neglect things consistently. So if you somehow assume that your UV theory does respect custodial symmetry, then you can discard all of the custodial violating operators, these and any others, with that assumption. But that is an assumption on top of your EFT. Right, I'm not sure if that's answering what you asked about.
Yeah, it basically is. I just thought it would be helpful for the students to hear along. Are there other questions?
Thank you for the lecture. I just wonder if you can find the best minimum between some lecture and last time using the CCW.
Sorry, something about lectons, but the sound is.
Sorry.
Can you say that again?
Yeah, I just wonder if you can find the last time lecture best minimum between some using this kind of CCW.
Sorry, it's still very difficult. You find that custodial vector?
I think he's asking about the West Semino-Witten term.
Yeah.
Oh, the anomaly, all right. Yeah, we're not. Yeah, sorry, I don't have much to say about that term. It's true that there is that there's topological terms that you also consider when you look at these series. And that's actually a very interesting question that I myself haven't worked out, but I don't know if it will have some interesting phenomenological consequences when you go and look at what would that be for Higgs effective field theory. Yeah, for these lectures we won't be talking about that anomaly piece, but it's you raised a very interesting point there.
Okay, other questions? Maybe we should break now and take a 20-minute break. We'll come back in 20 minutes, Rodrigo.
All right, thanks.
Okay, thanks for your lecture. The 35, yeah, we'll be back.